An essential part of our failure prevention analysis is the system of process class definitions. These are based on actual statistical process capabilities to given specification limits. Of course, our objective in each case is to achieve A-class levels for all process operations affecting statistical capabilities for each characteristic. This is less than 80% of assigned tolerance and capably centered. A B-class process is capable for statistical range, but in need of adjustment within the specified limits. C-class means not capable to required statistical criteria. Bracketed class letters indicate dynamic process variables. The first chart shows the statistical capability for thickness of core steel used in the matrix material. Please note that this and all succeeding charts will show both the specification limits, which are the yellow lines, and the statistical or plus or minus 3 sigma capability limits, which are the red lines, and which encompass 99.7% of all parts produced. These also will show process normality, which is indicated by the curves, and process capability will be shown as a percent of assigned tolerance, which determines process class. For core steel, which is a vendor control item, we show a 45% of tolerance capability, which is an A-class item. The finished failure prevention analysis form shown for the 2.3 cylinder head gasket shows both our initial and final capabilities. Note the 2 white columns, the process class columns, and the distributions of X's under the A, B, C process classes for each characteristic. The right column shows status after actions to optimize variability. Note the moves from the C and B to A-class levels. For these key characteristics, a series of 23 capability studies were performed, including repeats. Our approach on studying process variability primarily involved basic average and range analysis. We used the standard Ford chart form since these simplified capability determinations. Essentially, we sampled from each process operation through time, tested for normality, and reviewed results for any indicated actions.
Al Kavanaugh describes some of these actions during the question and answer period.
Because we have identified improvements that could be made in our process, we also identified those areas in our process that we would have to control better in order to achieve these improvements. We didn't really know what our capabilities were until we got in and started to statistically analyze what was happening. Once we did this, we were able to zero in on those parts of either the tool or the machine that would require maintenance, better maintenance, in order to achieve our quality goal. The tooling and the processes that we're using today are basically the same processes that we've been using for years. We've just found out more about them. We've always used progressive tools at our unit. And the one thing that has changed at our unit is employee involvement. There has been a few changes in feeding of materials to our equipment that has been a direct result of the input of our quality circles. These changes has helped to reduce the operator fatigue that comes from running some of our processes.
Our total quality assurance approach using statistical methods follows that suggested by Dr. Deming and Dr. Chambers. Of course, these illustrious gentlemen also point out that implementation takes time and patience. In our case, implementation has been accelerated with strong commitment from our workforce and support functions in accepting change from a detect to a prevent mode of operation. Most of our training with management and hourly personnel has been done on the job. Over the past 6 months, approximately 40% of my time personally has been spent on familiarizing line and support personnel with these techniques and approaches. To facilitate training on the floor, we are upgrading all quality control check forms to statistical control formats. This approach has routinely familiarized operators with charting. And we have provided classroom training to all manufacturing management personnel to assure familiarization with statistical applications. In quality assurance, 4 additional salaried personnel are now qualified in these statistical methods. With the recent addition of technicians, we now have a direct interface with engineering and increased capabilities in manufacturing of implementing statistical systems. Our Quality Circles program has been a good vehicle for training. The 2 inspection circles alone have been provided the equivalent of 7 hourly sessions each on both statistical methods and analysis of process problems. In addition, all circles have been familiarized with data collection and analysis techniques. These P charts shown are maintained for increasing prevent orientation, which is an important objective of our quality circles. It should be noted that the transfer of first piece inspection responsibilities from quality assurance to manufacturing was coordinated through circle activities in problem analysis.
The presentation continues with a discussion of statistical techniques.
Statistical data in cause and effect diagramming has been more effectively shown direction on corrective needs. This is a standard analytical tool used by our circles. The differentiation between system and local causes or process variation affecting ability to meet specified design criteria has been well explained by Dr. Deming and Dr. Chambers. Our evaluation of problem operations to date appear to confirm their findings that about 80% of abnormal variability is due to system causes and less than 20% to local causes. And we have a number of examples showing the direct relationships of quality and productivity. The recent rebuild of our coder is a good example. This project was cost justified on the basis of such analysis to improve productivity through the reduction in rejects.